Alright, so in the last video we set up our typical kind of problem to solve in a operations research. And so we have our data here for our windows. We have these two products, product 1 and product 2. And we want to see how to set up this problem in order to maximize our profit. So let's go ahead and kind of check things off here. What are the variables that we need? Well, our decision variables are how many batches of product 1. So decision variables. How many batches of product 1 should we make? We'll make that X. And then similarly, how many batches of product 2? And let's make that Y. Good. Then our profit will be Z, and so we're going to call that the Z is going to be our objective function. So the objective function, so let me spell that correctly here, objective function in this case is going to be the profit, which we'll say is Z, and so Z is going to be $3,000 times X plus $5,000 times Y. So I'm going to abbreviate that by 3X plus 5Y, and then we'll make a note that this is in thousands. All right. So this is the function that we want to minimize or maximize, of course. So we can't maximize, or we can't just build as many X and Y as we want. We have some constraints, and so what are those constraints? Well, it takes 1 hour per batch. Per batch 1, for batch, how am I going to say this? It takes 1 hour per product 1 batch in plant 1, and so I can't make any more than 4 hours worth, and so that means that my first constraint will be that 4x has to be less than or equal to 4, right? And now in plant 2, it takes 2 hours per batch of product 2, and so therefore 2y is going to have to be less than or equal to 12. And then finally, we have 3 hours per batch 1, or per batch of product 1, and 2 hours per batch of product 2. And if I sum those together, I should only have, I should have less than or equal to 18. So again, that was 3x plus 2y would have to be less than or equal to 18. And furthermore, we have another constraint that we didn't specify, and that is that x and y should be greater than or equal to 0. Good. And so this is now our problem. We want to maximize Z given these constraints. Okay, and that's going to be typical. Good. Now, how are we going to do this? Well, we said that in calculus, right, you're either going to look at your critical points or your boundary points, right? Those are the two things you have to check. Well, let's see. If my profit is, if my function of x and y is 3x plus 5y, what's the gradient of f? Right, because we're looking for the critical points, so the gradient has to be 0. But in this case, the gradient, is going to be the partial derivative of f with respect to x, which is just 3, and then partial derivative of f with respect to y is just going to be 5. And so this is my gradient function. It's never 0. And so the gradient is never 0. And so we have no critical points. And so therefore we only have one other option. Thus, the optimal solution lies on the boundary our domain. Okay, so now let's take a look at our domain. Our x is less than or equal to 4, y is less than or equal to, well, I guess x is less than, let's simplify this a little bit, right? Because this says, let me see if I can get that off to the side here. Maybe I'll put this in orange or purple, whatever that color is. X is less than or equal to 1, y is less than or equal to 6, and then 3x plus 2y is less than or equal to 18. So let's put those on my plane here. Let's draw a little picture. Okay, you'll remember those three constraints. If I move this up, why doesn't this move up? There it is. Okay, so here's our domain. X and y are positive. X is less than or equal to 4. Okay, I see I've made an error already. Let's go back up to our chart here, and that's a 1, not a 4 in my table. So I made a boo-boo. I'll show you right there. So because that's a 1, this should have been a 1 here and not a 4. And so I need to erase that. Good. And so x is less than or equal to 4. There we go. Sorry about that. Okay. Now I think we're ready to see if we can plot this. So this is not going to be to scale. Let's see, 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. So x is less than or equal to 4. Okay, y is less than or equal to 6. So we're in this region here. And then where does the line 3x plus 2y equals 18, where's that going to cross things here? So let's see, if x is equal to 4, then we have 12 plus 2y equals 18. So 2y equals 6, so y is equal to 3. So this point is going to be 4, 3. So 4, 3, 4, 3. Okay, and then if, let's see, where's my other point? If y is equal to 6, then this is going to be 3x plus 12 equals 18, or x is equal to 4, is that right? So 6. Nope, that's not right. 3x equals 6. 3x equals, sorry about that. I'm still getting used to this stuff. 2. There we go. So we have 2, 6. Good. And so this line is also part of our domain. So this is now removed. This is now removed, and this is our domain. Good. All right. And now, finally, then we have to optimize our solution along this region, right? So let's take a look at some possible examples. So again, we're optimizing 3x plus 5y. Now, what happens along the x-axis? Along the x-axis, y is equal to 0, and so this function just becomes 3x, right? And so the maximum would occur right here at the boundary, and so that's 3 times 4 is equal to, so at this point z is equal to 12. Okay, and then similarly, along the y-axis, x equals 0, and so then we're just optimizing 5y, and then so the optimum would be, or the maximum would be 5 times 6, which is 30, which appears up here. Okay. Oops, I lost my y-axis here. Oh well. Okay, and then finally, what happens along this line right here? Well, maybe I'll do this line right here. What happens along this line? Along this line, x is equal to 4, right? But then y is ranging from 0 to 3, right? So what's the optimum going to be there? Well, the optimization function then would be 12 plus 5y, and then if we put in 5 times 3, we get 15, right? So 12 plus 15 is 27. Okay, and then let's take a look at what happens up here then. Well, it's kind of misleading because I didn't really want that. I want this piece right here, right? And so that's where y is equal to 6, and then x is ranging from 0 to 2. And similarly, you can see, right, that if y is fixed at 6, that gives us 30. 30 plus 5 times x, and then x is ranging from 0 to 2. And so you can see that the maximum is going to occur when x is equal to 2. And so that would be 30 plus 10 is 40. Okay, so that occurs right here so far. That's giving us our max, right? Now the question is do we get a bigger value here? And you can double check that, but the answer will be no. And so our maximum is going to be 40. And one thing you might notice is that later on we're going to see that you don't have to check the entire boundary. You only need to check these corner points here. We're going to prove it later, but the optimum must occur at one of these corner points. And we saw that in this case we have this corner point solution giving us a z of 40. Good. All right, so I'm going to stop here if I can get this to work, and we'll move on to the next video. Let's see, for some reason this is not responding.